Well, that about wraps it up for Calculus 1, except for some minor details like the final exam. But I wanted to talk about where we are in the story, in the big picture. After all, the story of mathematics doesn't end right here. And since we're in the middle of talking about how to find antiderivatives, let me just start with that. There are lots of relatively elementary functions that at the moment we don't know how to find the antiderivatives for. Something like sine cubed of x. It's a fairly elementary function just built out of sine and a power, and at the moment we have no techniques to be able to find the antiderivative of that function. Or perhaps something like x times sine x. Just built out of sine x, an x, and a multiplication. We don't know how to find the antiderivative of that. Now, there are techniques to find the antiderivatives of both these things. Even more startling, right now, we already know how to find the antiderivative of any polynomial, because all you really need is the fact that antiderivative is a linear function, and you know the antiderivative power rule, so you could find the antiderivative of any polynomial. But we don't know how to find the antiderivative of any rational function. Let's say I just have x plus 3 over x squared plus 3x plus 2. We have no idea how to find the antiderivative of something like that yet, which is a little bit frightening because this is just built out of plus, minus, times, and divide. I didn't even use minus there, but we don't know how to find the antiderivative of that. Also, sort of looking much more broadly, we mentioned in a previous video that there are functions whose antiderivatives can't be written down in terms of elementary functions, and I gave you an example. E to the x squared. There is no way to write the antiderivative of this function in terms of functions you would recognize. And a question that's way beyond the scope of the calculus sequence is how do you determine which functions can be written down, their antiderivatives can be written down in terms of elementary functions, and which can't. That question has long been since solved, but we don't know the answer ourselves. I want to take a look at another question that we didn't raise in this course, and you may not even realize is a question, but it's lingering around from your older mathematics courses. Let's say I gave you the number 2 to the, let's say, 3.37. Now, just looking at that, we can see that this number is between 2 cubed, which is 8, and 2 to the 4th, which is 16. Okay, let's say I asked you to compute this number to 2 places after the decimal. The nearest 2 places after the decimal. Could you do it? So if you stop and think about what you know about powers, you may be able to come up with a clunky way of doing this, but it would take a long time. And that should bother you because this is just an exponential. And you've been working with exponents, I don't know how long, since middle school, maybe since elementary school. And it should bother you that you're not really sure how to do this. You could type this into your calculator and get an answer very quickly. So your calculator clearly knows. It's a very simple function. So if you don't know how to do it, that should bother you a little bit. This is a question that we will have a much better answer to, how to compute these things. Not that you have to do this manually, but we should know how. How to compute something like this is a question that we'll answer in calculus 2, as is how to find the antiderivatives of all these 3 things. If I asked you to find the sine of, say, 20 degrees to, let's say, 3 places after the decimal, could you do it? And I'll even supply you with pi equals 3.141592, as many decimal places as you need so you can change the 20 degrees into radians. Could you find sine of 20 degrees to, say, 3 places after the decimal? your calculator can do it. And you've been working with sine and cosine for probably quite a long time. I don't know when the first time was that you studied trigonometry, middle school maybe. So if you can't do it, that should bother you a little bit if you're not sure what to do. Now, if you think back to trigonometry and the trigonometric identities, if you know your double angle formulas and your half angle formulas, you can probably come up with a way of computing sine of 20 degrees to however many decimal places you want. But it's going to be very clunky. It's going to be very difficult to actually do in practice. And one thing you might want to do is, how would I do that in the first place? How could I figure out what sine of 20 degrees is using those trigonometric identities that I learned in middle school or high school or whatever it was? It can be done, but it's not an easy thing to do. But after some of the material that we learned in Calculus 2, these two questions are going to seem much easier. We have a much better understanding of some of the elementary functions that we've been dealing with for a long time, but don't really understand. If I gave you right now the curve y equals x squared, you know what that looks like. It's just a parabola. Here we are at the point 1, 1. Here we are at 0, 0. And I asked you to find the area underneath the curve. You would say, absolutely no problem. I'm just going to integrate x squared between x equals 0 and x equals 1. I'll do a definite integral. I'll use the fundamental theorem of calculus part 1, and that will give me the area under the curve. Let's say I asked you a different but equally elementary question. Find the length of this curve. If this was a piece of rope, right now, we haven't a clue how to do that. But after Calculus 2, you would understand how to do that. There'll be a lot of other problems in Calculus 2 that have this sort of geometric feeling that we'll be able to solve. It might not seem clear why we might want to do this, but let's say we take this curve and we spin it around the x-axis. So you end up with this sort of trumpet shape. I don't know if you can sort of visualize what I'm trying to draw here. If we take this curve y equals x squared and spin it around the x-axis, you end up with this trumpet shape. What's the volume of this trumpet shape, or the surface area of the trumpet shape? Those are things that we address in Calculus 2 also. Now, speaking more broadly, since you first started talking about functions, you've been talking about functions where a single variable goes in and a single variable comes out. Real valued functions of one real variable. At some point in some class you're going to be taking, that's going to get pretty confining. After all, there are many things which depend on multiple other things. Instead of just one other thing, they depend on multiple other things. The price of this commodity may depend on the prices of these two other commodities. The total amount of your total amount of income depends on the amount of income you get from your job and the amount of income you get from any investments you have. And so there are plenty of functions which depend on more than one variable. And there are plenty of functions where what comes out is not a single real number, but is in fact multiple real numbers. And the kinds of functions that we've been dealing with are just not sufficient to talk about those kinds of problems. So Calculus 3, in a nutshell, for those of you that end up in Calculus 3, is just going back and talking about some of the same kinds of questions we talked about in Calculus 1, but in this much more general milieu where you can have more than one variable going in and more than one variable coming out. It's been a pleasure, everybody. Have a great summer.